Welcome back to section 5 in chapter 2. In this section, we're going to be looking at something called higher order derivatives. Now, a higher order derivative is nothing new. Like, we're going to be using the same skills that we've been working on for the past few sections. We're just going to throw a little twist in it. It's more of a definition than anything else. In addition to higher order derivatives, we're going to look at a very basic and fundamental application of derivatives and second derivatives. And we're also going to look at one of the things that we can do with derivatives in our calculators. So this is going to be a fun, exciting lesson. So the first thing is higher order derivatives. What are they? A higher order derivative is simply the derivative of the derivative. So the first derivative is the derivative that we use. The second derivative is the derivative of that. The third derivative is the derivative of that. The fourth derivative is the derivative of that, and so on. We can go as many times out as we want. And so before we get into an example, let's look at the notation. We have notation for both Lagrange and Leibniz, and technically, like, y could be used for Lagrange notation as well. We don't usually, but we could. But the notation here for Lagrange, we have f of x is our function and f prime of x, it's a derivative. And then second is f double prime of x. Third, we have f triple prime. Fourth, once we hit fourth, we put the exponent in parentheses. Like, we make it as an exponent, but we use a numeral. But we put it in parentheses so it doesn't look like an exponent. This would be especially important if we were using y, because if we have something like y to the fourth equals a number or equals something, well, is that an exponent or is that a derivative? So that's why we would put the fourth in parentheses, which specifies it would be a fourth derivative. And then fifth, we could keep going. The general case, f n prime of x. And so we could use that. Leibniz notation, we always use numerals. So we have y, we have dy over dx. Then we have d squared y over dx squared. D cubed y over dx cubed. Notice that the numbers actually have different placement in the top and the bottom. Remember that we could actually split that out. This could be d5 over dx to the fifth of y. And so that we could actually have d over dx to the fifth of y. It's the fifth derivative of y, but the number gets distributed to the top and the bottom, and the y gets added onto it. That's why the placement's kind of weird, but that is what the placement is. And so how do we find these higher order derivatives? Let's start out with a function. Let's start out with f of x equals x to the sixth minus 3x to the fifth plus 7x to the fourth minus 4x cubed plus x squared minus 5x plus 11. That's an 11, don't worry, it won't be there for very long. So that's our function. We can take the derivative, it's just power rule. So the derivative of this, x to the 6th becomes 6x to the 5th. 3x to the 5th is 15. X to the 4th. 7x to the 4th is 28x cubed. Minus 4x cubed is minus 12x squared. Plus 2x minus 5. And see that, I think that was an 11 at the end, it's already gone. Doesn't matter. So that's the derivative. The second derivative is just the derivative of that. So 6x to the fifth, bring the 5 down, that's 30x to the fourth, minus the 15x to the fourth becomes 60x cubed, plus the 28x cubed. 28 times 3 is 84x squared, minus 24x plus 2. We could take the third derivative. Notice in a polynomial case, the degree is going down each time. The coefficients might be getting bigger and more obnoxious, but the degree is going down. So the third derivative, bring the 4 down, 30 times 4 is 120x cubed, minus 180x squared, plus 168x, minus 24, and the 2 is gone. The fourth derivative, (120 times 3, because the 3 comes down, will be a 360x squared, minus, oh, that's another 360. That's convenient. That is coincidental. That is not a every time thing. And then plus 168. Right, we could take the next derivative. It would go from a quadratic to a line. And so we could keep going. Eventually, with a polynomial, we are going to hit 0. At that point, all the derivatives after that are just 0. You don't have to worry. But that's how we go. We could take the derivative of something a little bit more exotic. We could have, say, f of x equals sine of 2x. So now we have to use chain rule. So the derivative here, f prime of x, is going to be cosine of 2x times the derivative of 2x, which is 2. So it'll be 2 cosine of 2x. And the next derivative of cosine is negative sine. Going to have to multiply by 2 again because of chain rule. So that'll be negative 4 sine of 2x. And then take the derivative again. Derivative of sine, it's cosine. Multiply by that 2 again for chain rule, so that'll give us negative 8. Negative 8 cosine of 2x. Then we could take the derivative again, get the fourth one. Multiply the cosine is going to be negative sine, so that'll make it positive. Have to chain rule the 2, so we'll get 16 sine of 2x. So again, notice as I'm doing the chain rule, the stuff inside the trig function stays the same. That is always 2x. That will not change. The derivative gets multiplied to the outside. We could have something like f of x equals 1 over x, which remember is x to the negative 1. Derivative gives us negative x to the negative 2, which would be negative 1 over x squared. Another derivative, multiply by negative 2, that gives us positive 2 x to the negative 3, which would be 2 over x cubed. Third derivative, multiply by the negative 3 gives us negative 6 x to the negative 4. So that'd be negative 6 over x to the fourth. We'll do the fourth derivative. Negative 6 times negative 4 is 24 x to the negative fifth, which can be written as 24 over x to the fifth. So that's higher order derivatives. It's simply taking the derivative of the derivative of the derivative of the derivative of the derivative. All the skills that we're using are the same as what we've been doing. Yes, we will get to ones that are harder when we have the skills to deal with those, but right now we're just looking at the idea behind them. And in the next section, we're going to get into some applications of derivatives, but there is one application that's so common, so important, that we're going to look at it a little bit in this section. And then, we'll keep looking at it next section and throughout the year. And that's the relationship between position, velocity, and acceleration. So if we have an object in motion, the position is a lot of times defined as s of t. It could be x of t. If it's a particle moving along the x-axis, it'll probably be x of t. If it's something being dropped, it'll probably be h of t. But the general position is s. Why is it s? Not sure, but it is. So that's the position. Well, if we think about the derivative, if we find the derivative of this, the derivative is the rate of change. What do we call the rate of change of a position? We call that a velocity. V of t is the derivative of the position. So if you have a position function, you find the derivative, that gives you the velocity. And we'll get into the difference between velocity and speed next time. And then what if we take the derivative again? Since we're looking at higher order derivatives here, what if we take the second derivative? Well, that would be the rate of change of the velocity. What do we call it when the velocity is changing? That's called acceleration. A of t, that's going to be the derivative of velocity, or the second derivative of position. So if we have position, we can find the derivative to get velocity, find the derivative again to get acceleration. So for a problem, let's say hypothetically I was standing on the roof and I dropped a watermelon. Not saying I would. You know what? It's October. Let's drop a pumpkin. I'm going to drop a pumpkin. So I drop a pumpkin. This pumpkin is going to fall, obviously, and the position function, the height of this pumpkin from where I dropped it, could be described by h of t equals negative 4.9 t squared. That's the position. Notice it's negative. The position is becoming negative because it's falling. It's getting, the position's decreasing. So the velocity, we could figure out the velocity at any given time by taking the derivative of h. What's the derivative? 2 times negative 4.9 is negative 9.8 t. Negative 9.8. That seems familiar from my physics days. Negative 9.8. I'm sure we'll be back to that. So that's the velocity. It's negative 9.8 times t. Then the acceleration is just the derivative of that. The derivative of negative 9.8 t is negative 9.8. Acceleration, 9.8, maybe our units that we didn't mention would be meters per second squared. Velocity is meters per second. The height is meters, because negative 9.8 meters per second squared is the pull of gravity. That's why in all of your height equations that you've ever had when you had a falling object, you had a negative 4.9 t squared, because that's what you get when you have the constant acceleration of gravity. But this is basically what you're doing here. It could be, oh, we want to find it at a certain point. We want to find it when t equals 1. You just plug it in. H of 1, negative 4.9 times 1 squared is negative 4.9 meters. Units are important here. If units are given, you need to have units in your answer. The velocity after 1 second is negative 9.8 times 1, negative 9.8 meters per second. And the acceleration at 1 will be the same acceleration that it is at every time, which would be negative 9.8 meters per second squared. A lot of times when we're doing higher order derivatives, we get the first derivative and the second derivative. We rarely go higher than that. And it's precisely because of this relationship. And in the next section, we'll see other things where the second derivative has meaning, but beyond the second derivative, the meaning gets a bit washed out. And so, lastly, let's see how we can find some numeric derivatives using our calculator. Now, a numeric derivative is like what we just found when we plugged in the value. It gives us the number, it gives us the value of the derivative at a certain point. A numeric derivative is not the equation. Your calculator will not give you the equation of the derivative unless you have one of the CAS ones, but those aren't allowed on a lot of tests precisely because of that reason. So let's find the numeric derivative. Let's use an equation that we can't figure out what the derivative is right now, because that's one of the times when we would find a numeric derivative. If the equation is either too unwieldy to be realistic, or it might just be using stuff that we haven't learned about yet. So let's use f of x equals e to the sine x. Now again though, it won't find the derivative of e to the sine x. However, it will find the derivative of e to the sine x at x equals 3. So to do this, we're going to get out our calculators. So you can go ahead and pause this and get it out if you need to, or come back and see it. I'm going to show you two different methods of doing this in your calculator. Both of which I would start out by entering the equation to y equals. A lot of times you're going to be using it more than one time, and so entering it into y equals means you only have to enter it once. So we're going to go to y equals, and we're going to enter the equation, e to the sine x. So we're just going to type e to the sine x into our equation. All right, then graph it. See what it looks like. That's what e to the sine x looks like if you never wanted to know that. Make sure you're in radian mode. And now we're going to go to the calc menu. The calc menu is going to be second and then trace. That's where the calc menu is. You've been here before, I can almost guarantee it, because you've used it to find the values, the zeros, the minimums, the maximums, the intersections. Now we have this dy over dx.
Now we're down to number 6. We're using number 7 this
Oh
year
my
as well.
gosh, it does have audio.
So we go down to number 6, and we pick it, then it wants to know where. We're going to find the derivative here for x equals 3. So you could scroll over to 3, or you could just type 3. Hit enter, and there's the derivative, negative 1.140038. So negative 1.14. That looks like about the right slope. It's angling downward at about a slope of negative 1. So negative 1.14 sounds about right. So that's one way to do it. That's one method. We have another method that doesn't involve the graph, So if we go back to the home screen, we can go into the math menu. And then in math, if we go down to number 8, nderiv, that's numeric derivative. We'll be doing number 9 later as well, the integral of a function. So numeric derivative, enter. Now this is one of the cool things about the newer calculators that puts it up right like that. The older ones, if you have an older calculator, it's going to go nderiv, parentheses, you have to type in the stuff in the right order. And if you have different types of calculators, the process will be slightly different, but it's going to still be about the same. So here we want d over d, our variable, that's x, d over dx of the function. We could type in the function here, go e to the sine x, or we already have it typed into the y equals. We can just go y1, that's alpha trace y1. But again, you could just type in the actual function there, and that would work out as well. And then at x equals, we're looking for it at x equals 3. Enter. Negative 1.140038483. So again, we got about negative 1.14. So either way we do it, we get the same answer. Now, this is not an exact answer. This is an estimation, but it should be very, very close. So those are two methods we can use to find the derivative on a calculator, either if we can't find the derivative, or it might just be just a boondoggle. It might be amazingly cumbersome to find this particular derivative. So there's that.
And that's what we have for this section. We have higher order derivatives. We have some relationship between position, velocity, and acceleration. And then we have being able to find a numeric derivative on our calculator. So this one, of all the ones that we've done, this one should not be the hardest. But keep working problems, keep asking questions, and as always, happy mathing.